All right, let's talk about something we use every single second, but maybe you don't totally understand. Electricity. Today, we're going to pull back the curtain on the invisible forces that power pretty much everything. We're breaking down the fundamental rules that run our world. Let's get right into it.
I mean, think about it. You flip a switch and boom, there's light. You plug in your phone and it just charges. It can feel like pure magic, right? But it's not. It's all governed by a few surprisingly simple principles. So the big question is, how does it actually work? Let's figure it out together.
So to get a grip on electricity, we have to start with the most basic thing it does. It flows. And that brings us to our very first key idea, current. Okay, so what is electric current? Well, the textbook definition is the rate that electric charge flows past a specific point in a circuit, and that charge is usually carried by tiny little electrons. We measure this flow in a unit you've probably heard of, amperes, or just amps for short. Now, to make this super intuitive, let's imagine a water pipe. This is going to be our go-to analogy. The electric current, the amps, is just like the amount of water flowing through that pipe. A huge gush of water, that's a high current. A little trickle, that's a low current. Simple as that. And this flow basically comes in two main flavors. First up, you've got direct current, or DC. This is a nice, steady, one-way street for electrons. Think of the power coming out of a battery. That's DC. And then you have its wilder cousin, alternating current, or AC. This is where the flow zips back and forth, constantly reversing direction. That's the kind of power you get from the outlets in your wall. Okay, so we've got this flow, but what's stopping it from just running wild? What's holding it back? Well, that brings us to our second really important concept, resistance. Electrical resistance is, well, it's pretty much exactly what it sounds like. It's a measure of how much a material fights against or opposes that flow of electric current. And we measure this opposition in a unit called ohms, which is represented by that cool Greek letter, omega. Let's jump back to our water pipe analogy. If current is the amount of water flowing, resistance is anything that squeezes or clogs the pipe. You can picture it as a really narrow, rusty section of that pipe. A big, wide-open pipe has almost no resistance, so water just rushes through. But a skinny, gunked-up pipe, that's got super high resistance, and it's going to be tough for water to get through. But here's the really cool part. Resistance isn't always a bad thing. In fact, we use it all the time. That orange glow inside your toaster, that's just a wire with really high resistance that gets incredibly hot. And the light from an old-school light bulb? Same idea. It's a tiny little filament resisting the current until it glows white hot. So for an engineer, resistance isn't a problem. It's actually a super powerful tool. So what actually determines how much resistance something has? It really boils down to four main things. First, the material itself. Some stuff is just naturally more resistant. Second, its length. A longer wire will always have more resistance than a short one. Third is its cross-sectional area. This one's a bit backward. A thicker wire actually has less resistance, just like a wider pipe is easier for water to flow through. And finally, temperature. For most metals anyway, the hotter they get, the more they resist the flow. And when we talk about materials, you have to see the mind-blowing difference between them. Just look at this. You have copper, a great conductor. Its resistivity number is absolutely tiny. Now look at rubber, an insulator. That number is a 10 with 13 zeros after it. It's not just a little different, it's an astronomically huge difference. And that is exactly why we make wires out of copper and wrap them in rubber for safety. And this really gets to the heart of it. In a conductor like copper, the electrons are kind of free-spirited. They can just move around easily, creating a current. But in an insulator like rubber, those electrons are held on super tight. They're locked in place, which means they block the flow of electricity almost completely. So we have current, that's the flow. And we have resistance, that's the opposition to the flow. The final piece of this puzzle is figuring out how these two are connected. And that's where this beautifully simple, incredibly powerful rule comes in, Ohm's law. So this law, figured out by George Simon Ohm, ties everything together perfectly, but it does introduce one new idea, voltage. So back to our water analogy, if current is the amount of water flowing, you can think of voltage as the pressure that's pushing the water through the pipe. More pressure, more flow. It's that intuitive. And Ohm's law basically says that the current you get is directly related to that push, the voltage, but it's held back by the resistance. That's it. More push means more flow, more resistance means less flow. And this perfect relationship gives us one of the most important and elegant formulas in all of science. Voltage equals current times resistance. V equals I times R. With just this one little equation, we can calculate, predict, and control pretty much all of electricity. It's the absolute foundation of all modern electronics.
And hey, if you ever forget how to rearrange the formula, and we all do, there's this fantastic little trick, the Ohm's law triangle. It's so clever. You just cover up the thing you're trying to find with your finger. So say you want to find the current, which is I. Cover up the I, and what are you left with? V over R. It's brilliant. Let's put it to the test right now. Let's say you have a standard 12-volt car battery, and you hook it up to a resistor that has 4 ohms of resistance. How much current is going to flow? Well, we just use our triangle. Current equals voltage divided by resistance. So that's 12 volts divided by 4 ohms, which gives us 3 amperes of current. See? It works every time. It's that predictable.
Okay, so that's the theory, but this isn't just some boring physics lesson, I promise. Why is it so important to understand current, resistance, and Ohm's law in the real world? Why does any of this actually matter? Well, because these ideas aren't abstract at all. They are quietly and constantly at work all around you, every single day. These rules are the reason the wires in your walls are thick enough not to catch on fire. They're why your electric stove can get hot enough to cook food. They are behind how every single tiny chip inside your phone or your computer manages electricity to do what it does. And if you zoom out, the scale is just massive. These same principles allow us to build enormous power grids that shoot electricity across hundreds of miles. They're used in heavy industry for things like welding metal together. And they're even used in medicine to read the incredibly faint electrical signals coming from your own heart with an ECG. So you see, current, resistance, and Ohm's law, they aren't just things you memorize for a test. They are the fundamental language of our modern, technological world. By understanding these simple rules, we've built everything around us, which really just leaves one question, doesn't it? Knowing the rules, what are we going to power next? Thanks for tuning in.